Chapter 4, we're continuing talking about probability. In 4.4 specifically, we're going to get into counting. The key concepts in 4.4, we're going to rely heavily on formulas here. We're going to consider 5 different methods for counting the number of possible outcomes with a variety of situations. Now, not all counting problems can be solved with these 5 different methods we're going to go through in this section, but they do provide a strong foundation for the most common real-world applications of using counting and probability. Here on this counting overview slide, I'm going to give you an example of why counting is such an important method to be able to know how to do in terms of probability. So as you may have discovered at this point, it's fairly tedious to determine all of the possible outcomes in a sample space. So for example, that boy, boy, girl, girl, boy, girl example. It's a lot to have to count up all of those different possibilities. Here's another example. So let's say we have a fast food restaurant. It has a meal special, $5 for a drink, sandwich, a side item, and a dessert. We have different choices amongst those different categories. So here for a sandwich, side, dessert, and drink. Then if we're asked how many meal combinations are possible, it's a lot to have to say, well, one combination would be chicken, cheese fries, apple pie, and Diet Coke. And you have to do that for every single possible outcome to make up all of our sample space. Well, when we're going to use counting or go through and determine all the different possible outcomes, we'd recognize there's 4 different stages: a sandwich, a side, a dessert, and a drink. Then within each category, we have all these different types of options. When we start to then use counting, which we'll do in this section, we can solve this without listing every single possible event in that sample space. The key to counting, though, is to recognize what situation we're dealing with and then therefore which formula to use. We're going to start out with the first, so the multiplication counting rule. In the multiplication counting rule, we have a sequence of events in which the first event can occur n number of ways. The second event, or subscript n2, can occur this many different ways. The third event, or n subscript 3, can occur this many different ways, and so on. Then if a situation like this is what we're trying to solve for, then we can calculate the total number of outcomes as n1 multiplied by n2 multiplied by n3. So this symbol here, or you'll see an asterisk or a multiplication symbol, this means n1 times n2 times n3, and so on for all the different events we're dealing with in the scenario. Let's jump right in and do an example of this. So we have a multiplication counting rule. We're going to apply this to a hacker guessing a passcode. In the scenario, when making random guesses for an unknown 4-digit passcode, each digit can be 0, 1, 2, up through 9. Now we're asked, what is the total number of different possible passcodes given this information? Well, given that all the guesses have the same chance of being correct, what is the probability of guessing the correct passcode on the first attempt? Well, to solve this, we're going to need to figure out all the possible attempts, but we definitely don't want to list all of these out. So in applying the multiplication counting rule, this is how we do it. First, we recognize there are 10 different possibilities for each digit, including 0, so 0, 1, 2, up through 9. So that's 10 different possibilities for each of the 4 digits. Then applying the multiplication counting rule for our event number 1, we have 10 different digits we could plug in here. For event number 2, we have the same. For event number 3, we have the same. Event number 4, we have the same. Where each event here is typing in one number. So event 1 is typing in the first number, event 2, the second number, event 3, the third number, event 4, the fourth number. So then following this rule, we multiply 10 times 10 times 10 times 10. So there's 10,000 different possibilities. So it's always important to go back and look at what questions were asked. We did answer this one now, so the total number of different possible passcodes. This next part of the question, given that all the guesses have the same chance of being correct, what is the probability of guessing the correct passcode on the very first attempt? Now, this is saying that we have one attempt, but we had 10,000 different ways of using that first attempt. So now the correct answer here, we have a 1 in 10,000 shot of getting this passcode correct on our first attempt. If we divide this out, that's really a probability of 0.0001. Now that we're more comfortable with this multiplication counting rule, let's go back and look at that fast food problem that we looked at initially. So now with our multiplication counting rule, we can solve this. To refresh you on this, we have 4 different stages: the sandwich, the side, the dessert, and the drink. For each of those stages, we have different amounts of possibilities. For example, for the sandwich stage, we have 4 different types of sandwiches. For the side stage, we have 3 different types of sides. Now, using the multiplication counting rule, we can say for this first stage, which would be the sandwich, we have 4 different possibilities. For the second stage, which is choosing a side, we have 3 different possibilities. The third stage is selecting the dessert. Here we have 2 different possibilities. For this fourth stage, we're choosing a drink, and we have 5 different drink options. Using the multiplication counting rule, we take this number times this number times this number times this number, and we get 120 different options. If we really tried to count up all the different possibilities without using that rule, it would take a while. We'd have to list 120 different possibilities. This is a much more user-friendly way of getting the same answer. So that was the multiplication counting rule. Next, we're going to cover the factorial rule. You'll notice there are examples we're going to go through together and also examples you can do on your own. So here for the factorial rule, we have the number of different arrangements where order matters of n different items when all n of them are selected is n factorial. Now let me explain what this factorial part means. So this factorial symbol, or an exclamation point, denotes the product of decreasing positive whole numbers. One special case you need to keep in mind is that when we have 0 factorial, that's really equal to 1. Now keep in mind, in the factorial rule, the order matters. So this rule is based on the principle that the first item may be selected n different ways, but then the second item we have n minus 1 different ways because we already used up one option in our first selection. So if we take n times n minus 1 times n minus 2 and so on, that is a factorial. Before you look at the next slide, try writing out 5 factorial, 4 factorial, and so on, and then go to the next slide and we'll talk through these. So hopefully you did this. For 5 factorial, it's really saying 5 times 4 times 3 times 2 times 1, and then we get an answer of 120. 4 factorial, we do the same thing. We get our answer here. Where these asterisks means multiplication. So then 3 factorial, 3 times 2 times 1, 2 factorial, 2 times 1, 1 factorial, and remember that special case of 0 factorial is also equal to 1. Depending on what calculator you use, you can have your calculator solve these for you. So I highly recommend you find the factorial option on whatever calculator you're normally using. You can also use Excel to get a factorial. Let's do an example now using the factorial rule. Here, a statistics researcher, maybe you, must personally visit the president of all these different polling companies. To be exact, there's 1, 2, 3, 4, 5 different polling companies this researcher is going to visit. In part A, we're going to answer how many different travel itineraries are possible. Then in B, if the itinerary is randomly selected, what is the probability that the presidents are visited in alphabetical order? Let's solve for part A. One thing I want you to keep in mind is you won't always be told which rule to apply to the scenario in your question. Here we should get an inkling that we're going to use the factorial rule because order matters as far as the visitations. We have to visit someone first, then second, then third, and so on until we visit all the different presidents of the polling companies. So here for part A, for those 5 different presidents, the number of different travel itineraries, where again, order of travel matters, is going to be 5 factorial. Where 5 factorial is equal to 120. Another way to think about this for yourself is that if you have the first travel opportunity, you have 5 different presidents you could go see. The second travel opportunity, you have 1 less, so you have 4 options. The third travel opportunity, you'll have 3 to select from. The fourth opportunity, 2 to select from. And then for the 5th travel opportunity, there'd be only 1 president left at that point. Now, you may be recognizing that this solution could also have been done by applying the multiplication counting rule. This is essentially what I talked through. So the first person can be any one of the 5 presidents, the second person could be any one of the 4 remaining presidents, and so on. Where the result again would be 5 times 4 times 3 times 2 times 1. I think one suggestion that might be helpful is that if you have 5 different events, it's good to write out 5 different lines and then be filling in the different options for each line or each different event. Let's go on to part B. So if the itinerary is randomly selected, what is the probability that the presidents are visited in alphabetical order? Well, here we could see that we'd have to go to H, then G, then N, then P, then Z. So there's only one different way we can travel so that we're reaching each president in alphabetical order. So for part B, we just solved initially that we have 120 different options. Here we're asked about the probability that the presidents are visited in alphabetical order. There's only one possible way we can visit the presidents in alphabetical order. So here we have 1 because there's only one different way we can achieve this alphabetical order, divided by the total number of ways we can visit these presidents. So that is our final answer for part B. Next, we're going to talk about permutations and combinations. The key question to answer when deciding between these two is, does the order count? So here for permutations, permutations of items are arrangements in which different sequences of the same items are counted separately. Let's do an example of this. So how many permutations are there in the letters of A, B, and C? Keep in mind this definition of permutations. This is where different sequences of the same items are counted as separate. So here to rearrange A, B, and C into all the different permutations, well, we could say A, B, C, A, C, B, B, A, C, B, C, A, C, A, B, and C, B, A. We're counting all these out, and now we know there are 6 different permutations of these letters A, B, and C. On the other hand, are combinations. Combinations of items are arrangements in which different sequences of the same items are counted as being the same. So remember for permutations, we figured out there are 1, 2, 3, 4, 5, 6 different ways that A, B, and C can be arranged. As far as permutations, we had 6 different permutations. Now, what about using this definition of combinations for this same example? Here, different sequences of the same items are counted as being the same. So in other words, for combinations, the letter arrangements of all of these are actually considered to be the same combination. So this example for combinations, we say there is 1 total combination. So remember this question we're asking initially, does order count? Think about that. One note before we talk about that explicitly, this means there are 6 arrangements of the same 3 letters when we're talking about permutations. What is this using factorial notation? Well, 6 is equal to what as far as the number 3 goes? So here 6 is equal to 3 times 2 times 1, or 6 itself is equal to 3 factorial. In other words, 3 is the total number of letters being considered. And from this total number of letters considered, we figured out there are 6 arrangements by taking 3 factorial. Let's make this more general here. So in this case, n, the number of items, is 3 for this example. More generally, we can say that for n number of items, they can be arranged in n factorial ways when we're talking about permutations. Now let's compare these two and decide, does order matter for each one? So for permutations, remember permutations position. So here we have this consonance, we have this alliteration. So permutations position. The positions of the items make a difference. The order matters for permutations. For combinations, remember combinations committee. Here you could use this to remember that with members of a committee, rearrangements of the same members of that committee still result in the same committee. So for combinations, order does not count. For combinations, order does not matter. Let's talk about the math behind permutations. To do this, let's use the FCR, or the fundamental counting rule, to develop the rule for permutations. FCR is the same thing we talked about initially, so it was that multiplication counting rule. So let's suppose there are 8 students running for president, vice president, and treasurer of student council. How many ways can these positions be filled? Well, here we have 8 different items because we have 8 different students. A symbol you'll see when working with permutations and combinations is this lowercase r. Here we have r is equal to 3 for president, vice president, and treasurer because we want to select 3 of the 8 students for these 3 different roles. In other words, r is the number we are choosing. So with the FCR rule, and again, this is what I mentioned for a tip for writing out these different events where this could represent president, this vice president, and this treasurer. So here we write these lines out to kind of help us think through the different possibilities. Well, here for this first possibility, we have 8 students to select from. For the second possibility, we're only going to have 7 students left. For the third possibility, then only 6 students remain. So here, using FCR, or the multiplication counting rule, we have 8 times 7 times 6, so 336 different possibilities to have these 8 different students fill these 3 different positions. Let's think about this example and then figure out the formula, the calculation for permutations rule. So first, to formally define this, for a permutations rule, this is when n different items are available and r of them are selected without replacement. So in other words, we had those 8 different students. We're going to put somebody in the presidential role. They're not also going to be eligible then for the vice president role. So that means without replacement. Then with this, the number of different permutations where order counts is given by this equation here. So here, the number of permutations is equal to n number of items factorial divided by the number of items minus the number that we're choosing, or the number that are being selected without replacement. That's all in parentheses, and that's also factorial. Sometimes you'll see permutations written like this, where it's subscript n, and then p, and then r, and you would fill in the numbers for what n is and what r is. Now, going back to this example with president, vice president, and treasurer, where we had 8 students to select from, let's try using the equation we just learned about. So using the permutations equation, we had 8 different students or 8 different items to select from, so 8 factorial. This is going to be divided by, again, 8 for 8 number of items to select from, minus our R value, where our R value is 3 because we have president, vice president, and treasurer. So 3 different items that we're choosing. So here, 8 factorial divided by then 5 factorial, because very importantly, this is in parentheses, is still going to give us 336. That is the same number we got, but we used the permutations rule. Let's try another example here with trifecta betting and horse racing. So in a horse race, a trifecta bet is won by correctly selecting the horses that finish first, second, and third, and you must do so in the correct order. In some year of the Kentucky Derby, let's say we had 19 different horses that were racing. In A, we're going to answer how many different trifecta bets are possible, and then in B, we're going to answer, do all the 3 different possible trifecta bets have the same chance of winning? Here we're going to ignore dead heats, in which horses truly tie for a win. Let's look at part A first. So how many different trifecta bets are possible from those 19 horses? Let's start thinking about our symbols for the permutation rule. So N is 19 because we have 19 different items to select from. We have 19 different horses. For the trifecta bet, we want to pick the first, second, and third place winner. That's 3 different things that we're choosing. So here our R value is 3. Remember, this is without replacement because one horse can't get first place and then also second place and then also third place. So we're not replacing the horse each time where a horse gets first, it's replaced back into the running, and then it gets second, and then it's replaced back in the running, then it can get third. So this is what we mean by without replacement here. That's an important detail for our permutation rule. Where, remember one of the first examples we went through with trying to guess the passcode, we could definitely put in 0000, right? So we were sort of replacing 0 back into the mix. Here for permutations, we're doing this without replacement. So let's use the formula for permutations and figure out the answer here. So here, N, we know that's 19. Here in our denominator, N, which is 19, minus R, which here is 3. So here we have 19 minus 3, that would be 16. So to get our final answer, we have 19 factorial divided by 16 factorial. So then we get our final answer here of 5,814 different possible bets are possible in this year of the Kentucky Derby. Let's think about part B of that question. So do all 3 different possible trifecta bets have the same chance of winning? Going back to our question here, we're asked if a bettor randomly selects 3 of these horses for a trifecta bet, what is the probability of winning by selecting California Chrome to win, Commanding Curve to finish second, and Danza to finish third? Well, here from the last part A, we just calculated there are 5,814 different possible arrangements of those 3 horses selected from the 19 horses that ran that race. If one of those arrangements is randomly selected, there's a probability of 1 out of 5,814 that the winning arrangement is selected. However, we're always thinking critically in statistics, so here we're talking about the probability of different horses. Well, there's other factors here that are at play. So though there are 5,814 different possible trifecta bets, not all of them are going to have the same chance of winning because some horses are just faster than others. So sort of a tricky question, but remember we need to be thinking critically in statistics. So yes, this is true, but we need to take into account that different horses come in with different training and different speeds. So truly the answer is no. Do all the different possible trifecta bets have the same chance of winning? The answer to that is no. Before going into combinations, let's talk about this. So recall with 3 items, we can arrange those 3 items in 3 factorial ways. Then we determine generally with n different items, we can arrange those in n factorial ways. Here, let's show that if we have 10 items, we can arrange those in 10 factorial ways using the permutations formula. Now, remember the permutations formula, n factorial divided by n minus r factorial. Here, I want you to decide what would n be and what would r be. Well, here n is 10. We have 10 different items. R, that's the number we're choosing without replacement. So here we're taking 10 items, that's n. We're gonna arrange them in all the different possible ways. In other words, we're taking 10 of those different items, but we're gonna place each one of them in one place. So here, using the permutation rule, we're gonna have 10 different items, but we're gonna have a spot for each 10 of them. So really, R is also 10 here. Plugging this in, we have 10 factorial divided by 10 minus 10 factorial. N is 10 here, and R is 10 here. Then remembering that 0 factorial, that special case, that's equal to 1. So 10 factorial over 1 is 10 factorial. So we essentially proved this using the permutations rule. Okay, let's transition now into the combinations rule. So combinations rule is when n different items are available, but only r of them are selected without replacement. Then the number of different combinations where order does not matter can be calculated as this. Where capital C is for combinations, again, we have this subscript n and r where we'd plug in our numbers. N is still the number of items, and R is still the number of items that we're choosing. And again, this is important in combinations, so only R of them are selected without replacement. So you'll notice this looks very similar to our permutations formula. However, in our denominator, we have R factorial because we need to divide out the rearrangements of R objects, where the rearrangements of R objects is R factorial. We're doing this with combinations because order does not matter. So we need to divide by R factorial. When we divide by a larger number here, then we're gonna have fewer combinations. That makes sense because order doesn't matter. And remember for our ABC example, we had 6 permutations, but we only had 1 combination. Let's do an example using this combinations formula. So here's the scenario. In a California lottery game, winning the jackpot requires that you select 5 different numbers from 1 to 39. And the same 5 numbers must be drawn in the lottery. Here, hopefully it's clear that order does not matter, so then we'd be applying the combinations rule. But keep in mind, you won't always be told which rule you need to apply in future problems. So look out for wording like this. So because the winning numbers can be drawn in any order, we can answer using the combinations formula how many different lottery tickets are possible and find the probability of winning the jackpot when 1 ticket is purchased. Let's look at A. So for part A, we need to figure out N and R. That's our main point with combinations and permutations. Thinking through N, we have 39 different numbers, so 1 through 39. What if this were 0 through 39? Well, then we'd have 40 different options. So be careful if 0 is included. But here we can go from 1 to 39, so N is 39. R here is the number of choices that we're making. So we have 5 different numbers that we have to choose. So then we know 39 is N and we know 5 is R. Using the combinations formula, we can plug these in. So n is 39, so we have 39 factorial. In the denominator, we have n minus r, that's 39 minus 5. That's in parentheses, also factorial. Then we multiply also this in the denominator by r factorial, so we end up getting 39 factorial divided by 34 factorial times 5 factorial. So for this answer, how many different lottery tickets are possible? Well, 575,757 combinations are possible given these constraints. To answer B, find the probability of winning the jackpot when one ticket is purchased. For part B, we're really saying we're selecting one ticket out of all those different possibilities. So that's really 1 over 575,757 different possibilities. Maybe you do know someone who has won the lottery. Typical lotteries rely on the fact that people don't know how small this possibility is, how small the probability is that we just calculated. Your book was poking fun in this way. This is why the lottery is sometimes called a tax on people who have not taken statistics. I think the book worded it even more harshly than this, but now you're one who has taken statistics, and who knows, maybe you could win in 1 in this many chances. I am not encouraging you, though, to go bet in the lottery. Save that money instead. All right, the fifth rule here in 4.4 is Permutations Rule with some identical items. So here, the number of different permutations, where again, the order counts for permutations, when n number of items are available and all n of them are selected without replacement again, that part of the definition is the same. But for this case, some of the items are identical to others. Here, to calculate the number of permutations, we have n factorial divided by this. Let me describe the denominator here. So this is where we have n subscript 1. This is how many items are alike. N subscript 2, again, how many items are alike. This k here just represents the total number of possibilities. So in other words, we're not going to stop at 2 items alike. We could go up to kth number of items alike. Let's do an example and plug in some numbers here. So for example, when designing surveys, pollsters sometimes repeat a question to see if a subject is thoughtlessly providing answers just to finish quickly. For one particular survey with 10 questions, 2 of the questions are identical to each other. 3 other questions are also identical to each other. Then we ask, for this survey, how many different arrangements are possible? And then, is it practical to survey enough subjects so that every different possible arrangement is used? So our solution here, we have 10 different questions with 2 that are identical to each other and 3 others that are also identical to each other. To calculate the number of permutations here then, we use this formula we just learned about. Let's try to figure out what these mean. Where n is the total number of items. So here, n is 10. We have 10 different questions, 10 different items. Now remember in the denominator, we're going to use this to factor out the numbers that are identical. Here, out of those 10 questions, we have 2 that are identical to each other and 3 separately that are identical to each other. Then using this formula, we're going to plug in 10 for n. This n subscript 1 can reflect the 2 questions that are identical to one another. This n subscript 2 can reflect the other 3 questions that are identical to each other. So really using this formula, we say 10 factorial divided by 2 factorial times 3 factorial, where 2 factorial and 3 factorial are in the denominator. Okay, so we're essentially using the denominator here to say that there are 2 ones that are identical to each other and 3 others that are also identical. So 2 factorial and 3 factorial are in the denominator. Again, we can use our calculator or Excel, and we figure out this final answer is 302,400. Now, we answered this first part here. For this survey, how many different arrangements are possible? Now let's answer, is it practical to survey enough subjects so that every different possible arrangement is used? Well, from what we just figured out, there are 302,400 different possible arrangements of the 10 questions. From that number, it really is not practical to accommodate every different possible permutation, because this would mean that we would need 302,400 different respondents to respond to our survey. As a ballpark range for typical surveys, the number of respondents is somewhere around 1,000. So to answer this question, no, it would not be practical to survey enough subjects so that every different possible arrangement is used. We're at the end of chapter 4 here. As always, let me know if you want to talk through any of the example problems in your student outlines. There's a whole lot of you tries, and I'm happy to talk through those answers. Let me know if you have any other questions at all, and I'll see you next time for chapter 5.